In this video, we're going to introduce a new single-stage amplifier called a common base amplifier. Common base amplifiers aren't going to see a ton of use in this class, but they are popular in a variety of applications. They have low input resistance, which is useful for interfacing with high impedance current sources or with very low output impedance elements like 50 ohm antennas. Common bases have interesting output impedances because they're potentially quite high. We won't see this in our analysis because we're going to assume RO is infinite for simplicity, but the impedance looking down into the collector is on the order of beta RO. However, the collector resistor falls in parallel with this very high resistance, so this resistor-loaded amplifier never exhibits high output resistance. We're going to analyze the small signal parameters of this amplifier, and as usual, we need to start by making a small signal model. Pause the video and draw a small signal model of the common base. Here's a small signal model where we directly substitute the hybrid pi model into the circuit. And here's a simplified version where I've rearranged the elements to make the analysis simpler. This is a pretty simple small signal model, so I'm going to turn you loose on the Rin and Rout calculations soon. As a reminder, for Rin we set Rs to 0 and RL to a proper value for the amplifier, and that proper RL falls in parallel with RC. We use a test voltage source to analyze this amplifier. Pause the video and calculate the input resistance. The input current in this amplifier is the sum of current in the GM generator and the current in RPi. Note that when I wrote this equation, I implicitly flipped around the direction of VBE and the GM generator, because I presumed the GM current was flowing out of the node at the top of the amplifier. Right? I add plus IGM here, which would mean current was flowing down this branch. So with that switch made, we can substitute in expressions for RPi and GM currents here, finding Vn over RPi and GM times Vn. And we can substitute those in because the input voltage directly controls VBE. This is the same pattern that we saw when we analyzed the output resistance of an emitter follower, and every other time that we've driven a resistor with a voltage, and every other time that we've driven an emitter with a voltage source. So it shouldn't surprise you that we can rearrange this expression to find that Rin is the parallel combination of these two sort of inverse resistances, being equal to 1 over GM in parallel with RPi. To find Rout, we let RL be infinite and set Rs to a normal value, and that Rs connects from the base to ground. Pause the video and try to find Rout. The GM generator gets shut off by Rs grounding RPi, which means that the output voltage source only sees RC. That's a quick calculation, but it would be more interesting if RO were finite. That would fall in parallel here, which would mean we'd see a left-right pattern looking up into the combination of RO and GM, with these two resistors as the tail of the left-right pattern. And as I mentioned earlier, that left-right pattern can lead to a Thevenin resistance as high as beta RO, which is interestingly high. Finally, we'll find the voltage gain. We let the source impedance be 0 and the load impedance be infinite as usual, and then apply a test voltage source. Pause the video and try to find the voltage gain. The output voltage is going to be minus IGM times RC. Because the current is flowing up this branch, the positive side of the resistor is here, and the negative side is here. So we get 0 minus VRC, which is IGM times RC. And we can find IGM easily because Vn controls the negative VBE directly. So unlike the last slide, I haven't implicitly flipped VBE upside down, and I haven't implicitly flipped the direction of this GM generator. I left all the negative signs in this derivation. And you can see that those two negative signs cancel in our expression for Vout. which is the sort of result that we would have seen on the previous slide. This means that our voltage gain is just GM times RC, because that's multiplied by V in here. Notice that this is a positive voltage gain, so the voltage at the output is in phase with the voltage at the input. That's an interesting change of pace that can have some nice properties in feedback or noise cancelling systems. So in summary, common base amplifiers have low Rin, which is useful in specialized applications. The common base Rout is more interesting if we allow for a finite RO, and our amplifier parameters are as shown here.